All right, these notes are about powers and exponents. So, exponents are a shorthand way to show how many times a number, called the base, is multiplied times itself. So for the longest time, I didn't know what the difference was between the word power and the word exponent. But exponent is that raised small number that's next to the base, versus that whole expression is called a power. So writing, 4 with a raised exponent 5, that's a power. 4 is the base, 5 is the exponent. So you have the base, you have the exponent. The base is going to multiply it times itself potentially over and over and over and over and over and over again, the exponent number of times. We're going to have some specific examples down below that hopefully make it even more clear. For the first thing here, there are some special cases. A number raised to the power of 1 equals itself, because it's just writing it down just that one time. But any number except 0 raised to the power of 0 equals 1 because it's the number divided by itself. So the reason 0 can't be raised to the power of 0 is because you can't divide 0 by 0. And if you don't know, you'll have to ask some electronic smartphone or smart tablet. There's usually a pretty witty response to that. So with some specific numbers, if we have 7 with an exponent of 0, we could call that 7 to the power of 0. That's how you would verbally read it. I actually saw IXL called it 7 to the 0th power. So apparently 0th is a word I wasn't sure before. And if it asked you to evaluate it or find the value or compute, you would say it equals 1 because it's 7 divided by 7. If we have 6 with a raised exponent of 1 next to it, you would say 6 to the first power. Or you could say 6 to the power of 1. And it means you just write down the 6 one time. So it's just equal to 6. That's its value, or evaluated, or simplified, or calculated, and so on and so forth. But the next two exponents have special geometric connections. If you have an exponent of 2, instead of just 5 to the power of 2 or 5 to the second power, you could say it's 5 squared, because it would be the area of a square with a side length of 5. But we could still say second power, 5 to the second power, or 5 to the power of 2. Those are perfectly valid. Now at this point, when I have more than just an exponent of 0 or 1, I might be asked a different task. I might be asked to explain or show its repeated factors. Well, what does it look like as a product of its factors? So in that case, I would write 5 times 5. Or I could be asked to evaluate it or compute it, and so on. The value would be 25. Now when I do have an exponent of 2, if the base is a whole number, then the result is called a perfect square. And so if you're evaluating if a certain number is a perfect square, you can see if you can find something where a base to the second power will equal it, or you could see if you can find something that's below it or just above it as far as perfect squares, and yet itself would not be a perfect square. I'm getting some blurriness here. Let's see if I can. Sometimes if I press the undo, some of the blurriness goes away. Hopefully we're going to be okay for a bit. Okay. If you have an exponent of 3 that also has a geometric tie-in, you could call it 4 cubed, because it would be the volume of a cube that has an edge length of 4. It could still just be called 4 to the third power in a similar fashion as the above couple of examples, or 4 to the power of 3. And again, it could ask us to write 4 in expanded form, I've seen, or as a product of its repeated factors or something like that. In that case, you just write 4 times 4 times 4. But if it asks us to evaluate it, Then I'm going to do 4 times 4 is 16. I still need to do times 4. So 16 doubled is 32. 32 doubled is 64. Then I've evaluated it or found its value. Trying to get the blurriness away again. And then the exponents after that, they don't have geometric tie-ins anymore. So 3 with an exponent of 4 could be 3 to the 4th power, or 3 to the power of 4. Again, if they ask me to show its repeated factors, I might write 3 times 3 times 3 times 3. But if it asks me to evaluate it, I don't have to go back and forth, left to right rather. I don't have to say 3 times 3 is 9, then 9 times 3 is so-and-so, because I don't really care for doing 27 times 3. I might make mistakes, as opposed to if I pair up numbers. 3 times 3 is 9. The other 3 times 3 also 9. So I can multiply those out to get 81. I find that a little bit easier sometimes to pair things up. So here are our example tasks that I just verbally said above. If they want us to write something as a power, that means they want to see a base and an exponent. So this base is 4, and the exponent is 1, 2, 3, 4, 5 of them. 4 to the 5th, and that's all it means, no computing anything. If it asked us to write it with exponents or as a power. Or in exponent form, I think is another way. If it has a string of different numbers and it wants us to use exponents, I usually pick the smallest one, because remember we talked about organized lists. So I pick the smallest one, the smallest number, and in this case it's an 8. Count up how many I have. 1, 2, 3, 4, 5, 6. So 8 to the 6 times my next number is 9, and I have 1, 2, 3 of those. I do put a multiplication symbol in between those two. I'm getting blurry again, so let me undo. Let's see, write 7 to the 3rd power as a product of its factors. That you can write 7 times 7 times 7, not computing anything. Compute 1 to the 9th power. Compute means I am going to compute something. However, 1 times 1 is 1, times another 1 is 1, times another 1 is 1, times another 1 is 1, so on. Doesn't matter what the exponent is. 1 to any exponent is going to equal 1. First is evaluate 2 to the 3rd power. 2 times 2 is 4, times another 2 is 8. Now, if the 2 and the 3, the base and the exponent there, are flipped, it doesn't equal the same thing. It's not like multiplication where you can switch around the numbers. Find the value of 3 squared, or 3 to the 2nd power. 3 times 3 is 9. So clearly we can't just swap them out and get the same answer. Calculate 6 to the 0 power. I could show 6 divided by 6 if I want to show where the calculation comes from, but I don't need to because of this standard rule. It just equals 1. And the last example here. Determine if 125 is a perfect square. Show how you know. We used to do these notes live in person, and oftentimes a student would start by guessing 10 squared because they're really comfortable with that. And they know it's going to get pretty high up there, close to 125. But then you have to keep guessing to see if you get the exact 125 that you're looking for. So here I have my next guess is 11 squared is 121. So that didn't hit it. I do have to show that if I go to the next whole number and I square it, it's going to jump right past the number I'm testing. So in this case, 12 squared equals 144, goes past 125. Therefore, I've shown enough to prove 125 is not a perfect square. So typically if you see determine or prove or something like that, that means show work, to show how you know for sure that that's what we got. Oops. I tried to delete the word prove. It didn't work.